You're still taking the test, Egan? You're still taking the test? No. Oh. This is the lab, yeah. Yeah, so we have the 3 spreadsheets. I just want to build a connection between Excel and our studio.
Are we doing our studio?
Yes, yes, yes. Practice Lab 5 is the code on the canvas to download. So again, so we have organized here. So we have chapter 15, 16, and 17. So keep in mind, correlation establishes associations and the strength of associations in between 2 scale variables, which puts it basically at variance to the other hypothesis test where we had independent variables that work categorically with different levels. So correlation really means to establish associations, and associations between these 2 variables, the so-called correlation coefficient establishes the strength as well as the direction of this association, with a positive correlation coefficient indicating a positive correlation and the negative correlation coefficient indicating a negative correlation. The absolute magnitude of this correlation coefficient establishes the strength of the correlation with the conventions stated here. So we did the calculation of the correlation coefficient using this equation. Basically we're calculating deviations from the mean of each individual x and deviations of the mean of the individual y. That basically gives us to some extent the direction, because these will then calculate as a product, so they're multiplied, which basically means summing those products up will preserve the direction of the association. So this comes from the numerator. And then internally we have in the equation included a standardization step by dividing it by the square root of the product of the sum of squares, which to some extent standardizes it according to the direction and of the fitted line through that scatter. So that basically will then be important with regression, where basically this serves estimation of the so-called residuals, which is the distance of the individual points to the fit line or to the regression line. So this correlation coefficient we calculated here on the spreadsheet that accompanied class or module 21. So we're calculating here the deviations. We're calculating here the product of these deviations, and then in another step, we're calculating the sum of squares, which is basically nothing else but these individual deviations squared. Adding all of these squared deviations up gets us to the sum of squares of x and the sum of squares of y. Utilizing then the formula of the product, the sum of all this product of the multiplied deviations divided by the square root of the product of the 2 sum of squares gets us then to a correlation coefficient, which in the example of student absences and the corresponding exam grade was an inverse relationship that basically indicated that a greater number of absences associates with a smaller exam grade. We can also always quickly depict this as a scatter plot that basically gives us then a visual. This will be the practice lab in a second, yeah. Well, we have open practice lab number 5, the code that is posted on Canvas. This is the same example, yes. So this is the Excel spreadsheet we did in module 21. So we have here absences as a function of exam grades. So we're doing absences as a function of exam grades. Keep in mind, whenever you do a scatter plot, the first column will always be the x-axis, whereas the second one will be the exam grade, or the y-axis, the dependent variable. We can now quickly fit through by clicking on add chart element. We can fit the straight lines through, which shows here a linear function. Clicking on the trend line allows us to display an equation and an R squared value. So that's actually a pretty tight correlation of 0.72 with a decrease of 5.4% on the quiz with each absence. So remember how to interpret regression equations. So basically you have with the slope, you have the decrease, in that case, an decrease or the change in the dependent variable with each increment on the independent variable, which are here the absences. So now opening this up in R. So we have practice lab 5 completed.R as today's R code. We open this in RStudio. We have on line 1, we have clean the environment. That's just a comment. Line 2 essentially is removing, as we did in past labs, removing a list of all objects in the environment. So it removes literally all objects. So control and enter allows you to, or control and return allows you to clean the entire environment with line 2. If you click next, so these commented lines, you don't need to run. So these are basically not necessary to run. Because comment, this hashtag, indicates that nothing will happen if you run that line. It's just a note to your future self that you remember what you did in the following. So if you click now on line 4 and you press control and return, this basically builds here with the data frame command, builds a data frame containing 3 different variables. And you see this reflected if you open this up. Good. If you open this up, you see here that you have 10 observations of 3 variables. And if you click on that little spreadsheet on the side, you see here that DFM22 contains exactly the same data we had in Excel. So what the following does in essence, it allows you to inspect your data set. So if you click on LS, it gives you basically a list of the variables contained, which is your absence, grade, and student ID. If you are now trying to confirm it and transfer it into a separate object, you can also do that. And you're doing this here with the R equal sign. So the smaller sign and the hyphen indicates to R that you want the object to the left of that equal sign to be what the object on the right represents. So DFM22 and absences, and we talked about this. This is how you attract, and this is how you address variables in your data frame. So you basically, if you just select DFM22 absences, you just get the absences. So it basically addresses only that variable. If you want to pack this variable into a new object that you call absences, you would do it in this format. So if you press here control and return, it basically creates a new object that is called absence, and that contains the 10 entries from absences, but removes it or copies it outside of your data frame. If you do the same exercise with grades, you can do this by running line 10. You could hypothetically transfer this from your data frame in the same format. And I just changed absences to grade because that was double. Yeah, sure. 11, line 11. You change absence to grade. You make it grades equal sign DFM22 grade. And again, in the same format as line 9, DFM22 grade represents only the only the grades that basically are contained in your data frame. So this is how you can individually, yes.
Of separating that, like when we do like line 9. You
Yes.
said that that's how you adjust the variables, but
Yes,
you said it's taking out something. What is it taking out?
it's extracting from your data frame whatever information you want to extract.
So like it's just like a list of all the absences.
It is a variable. So it is a variable is in essence, if you look only at the data entries, it's a list. Yes,
Oh, so it's like students absence grade and then it's
exactly. It just takes the entries and transfers the entries in a new object. Yes.
When I did that, where I highlighted it, did you click on control and return?
Yep.
When I did it, it says no.
It says no,
No.
null. Oh, then you did something incorrect. Does it say DFM22 grade? Do you have DFM22 in your environment?
Yeah.
Can you write ls? Can you run line 7? Yeah.
And then
Well, just press control and return. It should give you these 3 entries.
Yeah.
And then go back to DFM22 absences.
it worked for absences.
Then does it work for grade?
No.
Does it work for grade or for grades? Plural or singular?
But, singular. So that's really- Wait, I saw it. I some reason I did.
Yeah, R is unforgiving for this case.
Mhm.
Okay, then we have CoF1. So now it's getting interesting. So now we're coming to an actual correlation. So the whole exercise that we basically did in Excel by calculating the deviations, calculating the product of the deviations, and then using this to divide it by the sum of squares, which is basically consistent with this, which is F13, which is our product, sum of products divided by the sum of squares under square root. This is basically in Excel, you can do this just simply with the choral function, right? And we discussed the choral function in module 21. You can do the same function in R with the core function. What's different now is that you can take this core, you can basically pack the function, the entire complex of everything that is associated with core, you can pack into CoF1. That's what we're doing on line 12. We didn't change anything, we're just doing line 12. So if we're writing our CoF1, we get our correlation coefficient. So that's basically the calculated correlation coefficient. So if we do LS CoF1, so if we get, okay, that's bless you. So if we get summary, but what we also can do, we can use the LM function. And that's already the next level, that's already regression. So LM stands for linear model. So we're basically fitting our linear model that basically contains the grade as the dependent variable and the tilde that is here on line 13 between grade and absences indicates that to the left of the tilde you have the dependent variable and to the right of the tilde you have the independent variable. So LMDF grade as a function indicated by the tilde of DF absences is basically giving you a linear model of the association between those two. And R will automatically pack this now into the object fit1. Fit1 essentially is now an object containing all information of a regression model. So this is different than from what Excel is doing, because Excel basically builds here the equation for you depicts it nicely, but it doesn't really give you information that we may be interested in. So if you run line 14 in our studio, you basically get a very detailed overview of, bless you, of the regression model of grades as a function of absences. So you will see, and you remember how we looked at statistic output of various regression functions earlier in module and 20. So basically, you have here the linear model that is basically df grade as a function of df. We get here the so-called residuals. The residuals are basically the distance of the individual data point to your regression function. Keep in mind, this isn't residual. Yeah. So this is the residual. This is the so-called error. So this is the error and the deviations we have calculated if we're calculating the distance of each individual data point to the mean. If we are fitting a regression function through our scalar, we're minimizing the residuals and we're making this squared deviations, these deviations from the individual function, either it's the mean or it's now in that case the regression function. We're trying to minimize this. And this is the least square approach to fitting regression functions through scalar. So these residuals we actually mean to minimize. So this is how a regression function is being built. So now if we are looking at these residual characterization, we're basically seeing that this is depicted here as a summary. So we have a min, we have a max, the minimal residual and maximum residual. We have first quartile, third quartile, so that's 25th to 75th percentile, and we have median. So why a median and not a mean? Because the mean, per definition, needs to be the mean of a distribution of residuals. By definition, needs to be 0, because that's how it's calculated. Because it's calculated as the distance between the observed point and the predicted point. So the mean needs to be arithmetically perfect because it's a least square approach. You mean to minimize those, and you have as your approach, you minimize that. So the median here indicates that, so we remember that in a perfect normal distribution, the mean and the median is identical. If the median is now not 0, but the mean is by definition, we essentially will see a downward skewed distribution. So we see a left skewed distribution of our residuals, which indicates that the fit is not perfect and there are more shifting downwards than upwards. Secondly, we're seeing here the coefficients, and the coefficients are basically nothing else but our regression coefficients. So we have here in our exam grade example, we have here minus 5.4 as a slope, and we have 94.3 as our intercept. So these regression coefficients are also depicted here. So we have 94.3 as our intercept. This is stated here. And then we have DFM22 absences here as our slope. So this is minus 5.4. What we also get is the standard error of the estimate. The standard error of the estimate is determined by the residuals according to the respective inaccuracies that we see. And these residuals are in addition to that also characterized as a t-value. So if we have a standard error, it's easy to calculate the t-score and the corresponding p-value. So both correlation and regression. So regression follows a t-distribution. So what the p-value here indicates is that it's smaller than 5%. That means it's a significant slope. And here it also indicates that this is scientific notation. I don't know. I hope everybody is somewhat comfortable with those. That basically is 5.28 to the power of minus 0.8, which means it has essentially 8 decimals, 0 decimals in between 5.28. So this is a very small number, indicating here, according to the asterisk here on the right, that this basically is significant on a p-value level of 0.001 placebo. So the residual standard error is here shown based on the overall model. So this is on the overall model, on the overall predictive accuracy of the model. Is 8.28 or 8.828 is here the overall residual standard error on 8 degrees of freedom. And we know the degrees of freedom in a regression is calculated as the total number of entries, which is 10 for our example. Because we have in DFM22, we have 10 observations over 3 variables. And 10 minus, because we have 2 sum of squares, one for x and one for y. We can draw one redundant entry. That means we have 10 minus 2 determines the number of degrees of freedom on a regression. So we have a degree of freedom of 8. Then we have an R squared, which we know how to calculate, and we know this from chapter. We have this from chapter 16. So we know that that R square is calculated as the sum of squares of total, so of basically taking the dependent variable and calculating the sum of squares based on the deviation from the mean as an estimate. And these squared deviations summed gives us the sum of square total. So this is the overall sum of squares. This is just how we calculated standard deviations, how we're quantifying our sum of squares. So now, secondly, we need to calculate now sum of squares error, which is essentially our residuals of a univariate regression analysis. So we're getting the same aspect. So we're calculating a predicted, and this is using this equation that we have derived here from our univariate model. We're predicting the individual y based on the number of stressful life events. That was the chapter 16 example. This predicted will then be subtracted from our observed depression score, gets us to the inaccuracy of the predicted equation. So calculating now what the regression function has allowed to minimize in terms of residual error as a proportion of our total error gets us the R squared, also called proportionate reduction of error. If we're doing the same with a multivariable model, it follows the same outline. We're just using a more complex equation, which we have done here. And this information is basically all shown here. Then we have an adjusted R square, which basically penalizes the R squared for the number of groups and variables that were included. So we also have an F statistic. So regression analysis follows an F distribution. Basically here we have 1 prediction and 8 degrees of freedom. So we have a degree of freedom of these variables of 1, which is our 1 variable. So we have intercept and variable, 2 minus 1 equals 2 minus 1 is 1. So this is basically we're predicting it with 1 variable, and we have 8 degrees of freedom of the individual entries. The overall model is significant, the p-value is smaller than 5%. So this is the information that is contained here in our R object. So we can also plot this quite simply. Any questions to the regression output? I think it's quite important that you know what the respective items on output is. So we have on line 15, we have a plot code. And the plot code essentially allows you to quickly plot the associations. And I have embellished it a little bit. Oh, that's the wrong one.
Where did you change?
Yes.
So line 0,
Line 15
Yeah.
shows grade in percent as the number of absences. You have the same?
wait, line 15 to what?
Line 15
Yeah.
shows you the grade in percent as a function of the absences.
Right.
If you run in addition line 16, your plot was just amended with the respective regression function.
-0.
Well, because that's your correlation coefficient. It's minus 0.85. It's just rounded to 1 decimal.
Oh, but it's not wrong.
No, it's not correct.
So how did you get 6?
6?
Yeah, 0.6.
Oh, no, that was, if you click here, line 17 calculated this. It jumped forward, it took the next example. That's where the 6 comes from. It's minus 0.9, that's correct. So this is,
Mine also has 6. Is that not meant to happen?
okay, just rerun line 15 to 17, and it amends it. So this is basically how R computes plots. So basically you have 3 main functions. One is plot that basically creates this plot, and you can embellish with commands that are embedded in the code and the function. You can change the exercises, you can amend the X and Y limits. So with applying, you basically have a function that you can fit through your scatter plot. And then you can see the direction of the association. And with the text function here, you basically, with X equals 6 and Y equals 90, you give it the location. So you state the location in which you're pasting then your correlation coefficient. And this comes from our CoF model, which is right here in line 12, basically extracts that information and places it on the graph wherever you want to have it. So I'm not going to go in much detail in why these functions function the way they function, because that's probably on the scope of discuss. But I think generally, those of you that will use R at one point in time, you will find it useful. Hopefully will find it useful to have this code. So these are very simple codes, essentially, that allow to kind of approach data like that. Okay, so now let's move on to the example from chapter 16. So remember, we had discussions about how to build regression models, and we built 2 regression models. We built the first regression model was predicting the back depression score utilizing number of stressful life events in the course of a life subject's or patient's life. So we found a regression equation by basically using the approach calculating first squared deviations, utilizing these squared deviations to basically to standardize our outcome variable, and then utilizing these standardized outcomes variable parameter. No? So basically what you do, you are basically calculating deviations from X, deviations from Y. You calculate again your correlation coefficient, and then you utilize the association of a standardized Y hat to be calculated with correlation coefficient multiplied by a standardized X. So since the correlation coefficient has a standardization procedure inside, where you have the product of the deviations indicating the direction of the association, to some extent deviations per se. And you're dividing it by the square root of the product of the sum of squares of x and y, you have a standardization. So distance, difference from an individual point to the mean divided by a variability is in essence nothing else but the standardizations like we have done it for the standardization of scores in chapter 6. It follows the same principle. So we're getting this standardized y hat, and by calculating it for a standardized x. So we're standardizing the individual values, and by that we can predict standardized individual values. Using this then to calculate the individual point backwards. So we get here an x, 0, 1, and 2, and 3. We can calculate standardized x values. So now predicting set y hat allows us to then retransform, knowing the variability of our y of 9.35 calculated on the actual data, allows us to calculate predicted y values. And these predicted y values can then be used to quantify intercept and slope, because we know that the predicted y at the point where x equals 0 will be our intercept. And the difference between our predicted y where x equals 1 minus our intercept will basically give us the numeric value of the dependent variable from an increment of 1 plus u. So this is our slope. So we have calculated the slope here, and we can reproduce this here in R by basically running df_m23 on line 19. That basically allows us to look at the same data we have in Excel. So that's basically our 10 entries that show each individual. It shows us the number of events. It shows us the back depression score, and it shows us the sleep disturbance score that we will need for the multivariable regression. With CoF2, we're basically calculating the same correlation coefficient that we know already, that's 0.58. We've calculated this by hand in Excel. That's our 0.58. We can then, in the next step, go on and calculate our linear model, and this is fit2a. Summary fit2a is now basically giving us that regression model that we have built within Excel. So again, same layout. We have the formula that basically is the back depression inventory score as a function of life event. We have residuals that basically have a min minus 10.7 and the max of 11.2. With 25th percentile, 75th percentile, and we have a median with the mean by definition being 0. That means that now our distribution is a little bit skewed upwards. That means that our back depression inventory score is tilted a little bit upwards, as opposed to being following a normal distribution along the regression line. We see that our p-values, so again, same outline here with the coefficients. We have our coefficients built. We have an intercept of 9.5, which we know. We have the events with a slope estimate of 3.2, with a standard error of the estimate evolving around these two coefficients, with a t-value of 2.4, 1.9, translating in a p-value a notch below 5%. And we have here a p-value that is 0.08. And this is here indicated by R, and that's interesting. You remember when I told you, like, it's not everything about the p-value, it's really more about the distribution and the biological plausibility of what you're seeing. sometimes you may also accept the p-value greater than 5% if that is biologically justifiable. And here we have a p-value of 8%, and R still indicates this with a point and says like, hey, that one may still be borderline significant, but may still be valuable. Residual standard error 8.113, that's prediction accuracy on 8 degrees of freedom. It's 10 individuals, 2 variables, -2, 10 minus 2 is 8. A multiple R squared is consistent with what we have calculated here. And we have then an adjusted R square of 0.25. So this one is smaller. The adjustment for the number of variables included will always lower the R squared, with the rationale that if you include additional variables in your model, per definition, your R square always needs to increase. But it's not allowed to indefinitely increase. You need to curb it, and you're curbing it by the number of variables that you include, because if you include too many, you're basically overfitting model that doesn't make any sense anymore in any shape or form, because then they may be violating collinearity principles and whatnot. So there's a lot of thought work into how many variables and what variables to include that needs to be done. F statistic, regression follows the F statistics. It basically is here calculated for one variable and 8 degrees of freedom with a p-value of the overall model of 8%. So not significant. So, but if you remember, we were not satisfied. So we can then with line 26, we can plot the whole thing. Line 27 fits us a line through. Line 28 gives us a correlation coefficient. That's the origin left now. So there was the correlation coefficient that Dahlia commented on. That's the 0.6. And fit 2b, and this is where it's getting interesting. So that's the multivariable model that we have seen as an SPSS output in chapter 16. Here we're actually computing it ourselves. And we have now computed with lines 29 and 30, we have our first multivariable model, which is here depicted with the formula vector regression score equals as a function of events and the sleep disturbance score. It is robust to some extent against adjustments. We have a max of 4, we have a min of 4. The median is still a little bit higher, not exactly 0, but it's deviating to an extent that's justifiable. And we have then the coefficients included in our shown from our model. So we have the intercept has now changed. The intercept is now negative. We have anything that can help us?
Well,
Anything that can help us?
so I read as the graph out.
Okay. It's not working. That's not good. You got to run it again from the beginning. Just go back up. If you go a little back up, you just load the data frame again. Start with line 19 and go step by step by step. It will compute the vector. That's how I've set the code up. So we have here the coefficients that basically show here the estimates of the intercept is now negative. We have with increasing number of events, we have an increase in the back depression score and an increase in the sleep disturbance score. We also have an increase on our depression score, which also makes sense, right? So, but what happened now, this is interesting. So the standard error basically changed now, increased for the intercept. It increased for the events, but it is considerably small for the sleep disturbance score, which is also reflected here in the t-value and also in the p-value that is strikingly small. So essentially what happens now is our overall adjusted R squared, and if we look here, so residual standard error has decreased as well. Now it's 7 degrees of freedom because we have 2 variables with the intercept is 3. So it's basically, it's 10 minus 3. That gives us 7 degrees of freedom. Now we have a multiple R squared that is 0.9 and an adjusted R squared of 0.87. Of note, the decrease is smaller because both together basically give you a pretty accurate estimate. Also, the F statistic has now increased from 3.9 to 31.32 on 2 degrees of freedom, which are the two variables, and 7 degrees of freedom vertically for each individual. So it's 10 minus 3. The p-value here is far smaller than 5%. Therefore, we have a significant model with the sleep disturbance score. Just make sure that you know each component of this printout. It's a little bit more complex than what you will see in SPSS, but it also is much more rich on information. What you also can do, and this is now interesting. If you run line 33, I keep on talking about the residuals and how the residuals are important to pay attention to. So if you run line 33, and you see here, then little menu popping up, it says hit return to see next plot. So once you do that, you see here what in regression analysis is being called a diagnostic plot. Why are these relevant? Because you need to understand the distribution of your residuals, and you need to understand how do your fitted values. These are your fitted values of your dispersion score. How do these actually change across the entire range of data? And why is that important? Anybody an idea? Why could that be important? What is one of the major assumptions of regression analysis? It's homoscedasticity. Because if these residuals are really massively changing over the entire range of your predicted values, you're violating the principles of this being a linear relationship and this being homoscedastic. So you need to pay attention to that. And these residual plots are extremely important to do that. So you need to press return 3 times, 2 times. That's another way of showing this data as a so-called QQ plot. And you can do this repeatedly. Here you have a different way of showing this as standardized residuals. And here standardized residuals showing you the leverage. The leverage is basically nothing else but showing you which points actually have most weight in affecting the slope of your regression analysis. Yes.
Did you hit enter?
4 times, yes.
No, on there.
You click on the console and it goes enter 4 times. Then it goes through these 4 plots. So line 35, we have 4 more minutes to finish this. So line 35 is now a coffee paper cup study. Remember? 159 individuals get 159 cups. 53 of them have their name correctly on the cup. 53 have them incorrectly spelled out, and 53 have no name on it. Are they recycling or are they trashing it? So line 36 builds a matrix. We start then labeling the matrix until that matrix looks exactly how we had it in Excel. What we're doing next is we're running a chi-square test against our data. This is done with function chi-square test. We use the table. Always keep in mind, columns are the dependent variable. Columns are your outcome. Rows are your independent variable, as per interpretation. So if you run now a chi-square, and you put x2 in the console, this gives you now exactly that association that we have quantified in our Excel example. So we have a chi-square of 7.6 on 2 degrees of freedom. Chi-square degrees of freedom or columns. Remember, it's 3 columns minus 1, it's 2, multiplied by 2, 3 rows minus 1 is 2, multiplied by 2 minus 1 columns is 2. This is degrees of freedom 2. And the corresponding p-value that is smaller than 5%. We haven't quantified it, but R is quantifying it for us by building the function. What you can also do now is this x2 is now essentially nothing else but an object. And this object contains various parameters. So we can enter x2 p-value, and it gives you the p-value. So you can transfer this p-value in a report. You can do with this p-value whatever you want to do with this p-value. You can now also query the observed, which are here 25, 13, 14, just like we have entered it in the raw table. x2 expected. This is now our expected count. In essence, in exactly the same format as we found in Excel. We have 3 groups. We have 25, 13, and 14. That's 38. Plus 14 is 52. The 52 divided by 3 gives us 17.33. We have here in the trash category with 28 and 40, that's 68 plus 98 plus 9 is 107. 107 divided by 3 is 35.6 periodically. You basically get here the expected counts for trash groups. So you the expected basically gives you an estimate for the counts in the respective groups, as if there were no difference between the levels of the independent variable, which we know there was. And we can quantify this essentially by calculating chi-squared and by calculating the so-called residuals. And this is where the last Excel spreadsheet comes into place. And this is the spreadsheet adjusted standardized residuals. This is on your canvas. I owe this to you from last time. You remember how we calculated observed minus expected squared divided by the expected gives us the respective components of the chi-squared. We then basically calculating standardized residual and adjusted residual, standardized residual calculated O minus E, so observed minus expected divided by the square root of the expected. So you basically get an estimate of variability. You have adjusted residuals, the formula is stated down there. That basically allows you to calculate that adjusted for the number of rows and columns. Just quickly about that. So you get an estimate of these calculated residuals here with X2 $ residuals. For the practice lab, please just select everything with Command and A or Control and A for the Windows user, run it with Control and Enter. Hold on a second. Yeah, Control and L, please, first. Yeah. There's a little bit of an error in there. It's yeah, it's important that you go step by step through each line of the code. If you press Control and L and you're not going line by line by line, particularly for the chi-squared example, it gives you a hiccup.
So until where can I do like all a lot together?
You just go line by line by line, Control and Enter for each line, and you're going to be fine. Make sure that you get past the plots, the diagnostic plots. It's a little bit more challenging to practice like this time. All right. Thank you very much and have a nice evening.